Variance and standard deviation, these measurements essentially show us how spread out our data values are. So when you think about like measures of central tendency kind of zero in on the average or the center, or what these data values are kind of revolving around. So they're kind of focusing in on the average, whereas variance and standard deviation are then going from that average and then measuring out how far the data values extend from that point. Okay, so there's kind of a neat relationship between central tendency and variance and standard deviation. Central tendency is kind of where we start these measurements for variance and standard deviation, but instead of measuring where they're centered around, it measures how far spread out they are from the center. Okay, so when we talk about variance and standard deviation, here's the formulas for each of these. Variance is denoted as sigma squared, and that's lowercase sigma right here, that thing that looks like a circle with a little visor on it with a little hat. But that's sigma squared, and so what we have is x sub 1 minus x to the bar over it squared plus x sub 2 minus x sub bar, and just keeps going. And essentially what we're doing, the reason that that dot 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 is there is essentially we're using up all of our data values. And then the difference here between variance and standard deviation is really just a matter of taking the square root of each side of the variance. So here, if I were to take the square root of each side, on this first side I'd be left with just sigma, and on the second side I'd be left with the square root of this whole thing. Okay, so really it's the same formula, except standard deviation is one step further, where we actually take the square root. And standard deviation is used far more often than variance is. And as we look at these formulas, that x with a bar over it thing that we see popping up all over the place, that's just our mean. Essentially, x with a bar over it is like the average of x, saying the average of x equals the mean. Okay, so when we see these x with a bar over it, we're talking about the mean. So this is the mean, this is the mean, this is the mean. Okay, x sub n is each data value. So when we see something like x sub 1, we're saying, all right, the first data value. X sub 2 is the second data value, the third data value, the fourth data value, and so on and so forth. And that's why that dot 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 is there. We don't know how many data values we have until we get an example. We just use each of them. All right, and then n is the number of data values. So essentially what's happening here is I'm taking the first data value minus the mean, square it, plus the second data value minus the mean, square it, the next data value minus the mean and square it, and I do that with each of my data values. Then I add up all those squareds that I just got, and then I divide by how many terms I have. So it's similar in nature to how we approach other things in terms of the mean. It's got a little bit of that thrown in there as we're dividing by how many we have, but it's just each data value minus the mean and square it, add them all together, divide by how many we have. Okay, for example, if I look at something like this, and this is an example that we've done previously, the first thing we always need to identify if we're going to do variance and standard deviation is the mean. So for this one, again, we've already done this previously, and when I identified the mean for this one before, it was 122. Okay, so that becomes really important, so I'm going to use that 122. So I'm going to find variance first, because it kind of just happens first. So I'm going to say sigma squared equals. So what I do is I take the first data value, which is 104, I subtract the mean, and I square it. And then I'm going to add, and now I take the next data value, the 117. I subtract the mean, and I square it. And then I do the same thing with the next one, and I just keep going until I've used up each and every one of these data values. And so after I have all those written, wow, that was a really ugly line that I just drew. Let me try that again. So after I have all these written, I just divide by how many data values I have, which in this scenario is 8. Okay? So I have 8 sets of these things in the numerator. And now it's really just a job for my calculator. Just be careful as you do this. The 104 minus the 122, that's going to be a 16, 17, 18. Well, really a negative 18. The negative's not really important because once we square this thing, it's going to be positive anyway. So I square it and I get 324. So let me write that down. I'll just do this in a couple different steps. So I've got 324. Plus the next one, that gives me a difference of -5, and then I square that. That's a 25. The next one is the same as the first one. That's a 324. The next one, 136 minus the 122 is a 14. 14 squared is 196. The next one, the 189, this was my outlier before when I looked at central tendency. So this one's a little bit out of the ordinary, but that's okay. When I subtract, it gives me a 67, and when I square that, it gives me 4,489. So again, I'm just working each of these out. The next one, 109 minus the negative 122 is a -13 squared, which is a 169. The next one, the 113, that's a 9, or -9 squared, which is 81. And then the last one, once again, we have that 324, because it's still the 104 minus the 122 squared. Again, it's all over, it's all divided by the 8. And now I just keep going, so I keep simplifying these things. So I'm going to add that numerator. Wow, that was a really ugly looking equal sign. So I add that numerator together, so I add all those up. And when I do that, it gives me 5,932 over the 8. And now I divide, and it gives me 741.5. Okay, so my variance this time, so variance is denoted this way. The variance is 741.5. And now from here, the standard deviation, I'm obviously not going to plug it all back into that formula. I'm just going to do the same formula and take the square root at the end. So really all I have to do is take the square root of the variance, and that gives me, for sigma, for the variance, it gives me 27.23. Okay, and so what this kind of shows me, and as we do more examples of these and we look at different variances and standard deviations, you're going to find out that the more spread out the data is, the larger these values are. So something like a 27.23 for our standard deviation, when we're talking about something as small as bowling scores that can only range from 0 to 300, that's a pretty significant difference and a pretty significant jump, which means these are fairly spread out. And really the culprit of that is this guy right here. It's that outlier that we saw before. And so not only does that affect the mean of this, but it also affects the variance and the standard deviation as well. Okay, so again, variance and standard deviation, it's just a quick way to see how spread out this data is. If we have a standard deviation that's very low, it means all the data values are clustered pretty closely together. Okay, and we'll take this a step further as we start to look at normal distribution curves and how the standard deviation is plotted in respect to the mean as we start to do normal distribution. But there's variance and standard deviation. Okay.